Gabriel Kron's Universal Engineering. 5th Popkov International Alexander Bogdanov Institute, Ekaterinburg, Russia. In March 1968, in a small American town Schenectady of New York State, there passed away Gabriel Kron, a scientist and engineer, whose ideas still agitate explorers in different countries of the world. A memorable article, placed in this occasion in journal Elektrikestvo, 1, noted merits of Kron as a pioneer of tensor analysis application in electrical machines and networks, and originator of generalized theory of electric machinery and diacoptics, the method of piecewise solution of large-scale systems. However, such view about Kron's works wasn't formed at once. In 1950, in the same journal Elektrikestvo 2, there was published a letter by Aber and Eve about Kron's works on tensor calculus application in electrical engineering, where the author wrote, "Kron's articles have made an undeserved impression on those not well enough acquainted with tensor mathematics, and also predisposed to obsequiousness at American sensations and editorial staff, sharing the author's opinion about methodological solidity of Kron's concepts, called up the readers for their critical analyses. Kron's works provoked acute discussions not only in our country. It was in particular caused by the fact that his ideas were based on engineering intuition, not always backed with strict proofs. Both this circumstance and the use of mixed mathematical and electrotechnical nomenclature in Kron's works scared pure mathematicians away from his works. From the other hand, Kron supports his reasoning with fundamental concepts of contemporary physics and mathematics, with application of tensor analyses in an unusual form which prevents an engineer, having ordinary qualification, from gaining an understanding of Kron's ideas and putting them into practice. Kron himself wrote about his theory the following: 3. When in the beginning of 30s, the author appeared with the entire tensor and topological theory of rotating electrical machines, and in some years, with the tensor and topological theory of fixed electrical networks, he came over a very unpleasant surprise. In most technical journals, new concepts invented by the author were absolutely unexpectedly and vigorously announced useless and erroneous. From the other hand, the some workers of Institute of Advanced Research in Princeton, Ofblin, Envale, J. von Neumann, and some ex-workers of the Institute, Boffman, Planjevan, and others, persistently advised the author to keep on further investigation. Even Einstein told to the author that he knew about his works from his collaborators, as the latter in his practical problems used Einstein's non-Riemannian dynamics of the general theory of electric and gravitation fields. The opinions of the respected scientists had nothing in common with absurd statements of that group of engineers. Although in his works Kron utilized the language of electrical engineering, he repeatedly underlined that the nomenclature was not obligatory, and his method could be stated in the language of the most modern mathematical theories, such as algebraic topology, geometry of differentiated diversities, homologies and cohomologies groups, not to mention usual tensor and matrix analysis. Kron's works, comprising 5 monographies and more than 100 articles published during 35 years, found a broad response in foreign literature. In numerous works of various authors, his methods were applied to most different problems. In a number of countries there exist special scientific societies of scientists developing tensor methods, Tensor Club in Great Britain, or Exploratory Association of Problem Geometry in Japan. In home literature, Kron's works became far less popular. Only in 1955, considerably abridged, there was translated into Russian his short course of tensor analysis for engineers electricians, based on works of 1932 to 39-4, and in Russian variant called Primenение tenzornego analyza v elektrotechniki. 5. Numerous articles in various foreign journals were still almost inaccessible, and without knowing General Kron's methodology, it was pretty hard to understand them. In 1972, there was made an attempt to fill in the gap by publishing Kron's monography, The Piecewise Solution of Large-Scale Systems, Diacoptics, 6, in Russian, that generalizes the author's research of many years. However, a very laconic style of the narration that presupposes awareness of previous works of the author, still left no hope to become proficient in tensor methods to the addressees of the work, to engineers. Finally, in 1978, there was published a translation of volumetrical Kron's work, Tensor Analysis of Networks, 3, published in original as early as 1939. In 1985, there was also published a book by Apetrov Tensor Methodology in Systems Theory, Tensornaya Metodologia phi Theory System, 7, where Kron's ideas are given in a very clear form, and there also have place examples of economic systems calculations with the help of tensor methods. The bibliography given by him shows that Kron's methods are still not widely spread in our country. This review article aims to acquaint readers with Kron's personality, to attract attention of scientists to wealth of his ideas, to show that importance of his work never decreases, more than that, it will constantly grow. Gabriel Kron, the eighth and the last child in the family, was born on 23 July in 1901 in a small town of Nagybanya, later renamed into Baia Mare, in a distant district of the Carpathians in Hungary, Transylvania, which later became a part of Romania. 8. Kron's thirst for knowledge and his purposefulness became apparent as early as at his school age. In high school, he intensively studied physics and mathematics, found much time to study astronomy, stenography, and languages, English and German. Being a high school boy, Gabby, as his friends called him, was invited as a house teacher to Felsabani, 7 miles away from home. He kept on teaching until he finished school, every day overcoming a 14-mile way. At 17, Gabby was already able to work hard. He was teaching till noon, practicing stenography from 1 till 2, solving algebraic problems from 2 till 3, studying French from 3 till 4, doing physics from 4 till 5, translating from German from 5 till 6, and so forth until 10 o'clock in the evening. In June 1919, G.K. Kron finished the high school and got a diploma. The question arose, where to continue further education. Following the First World War, Austro-Hungary fell to pieces and Transylvania became a part Romania. Kron didn't know Romanian language, so he decided his future to be connected with other countries. But he needed money to continue education abroad. Little money and hunger for studying were brought from war by an elder brother, Joseph. Gabriel talked his brother to go study to America by promising that within 1 year he would make him prepared for examinations and getting high school diploma. In the end of October of 1919, Joseph got down to intensive studying. Gabby picked for him not more than 10% of pages from the books necessary to read, and only them was studied by Joy. In the end of January, Joy passed exams for 4 grades, in April for the 5th and the 6th ones, in June for the 7th and the 8th, and in August he passed exams for the whole high school course. The way to America was now open, and started on from Antwerpen. In January of 1921, the brothers arrived at New York. In September they set to studying in the University of Michigan, at the same time working for living and studies. Gabriel washed dishes in a restaurant. Joy worked in a fur shop. At the last but 1 year in the university, Gabriel wrote a small work, Fundamentals of New Cosmology, where he tried to consider the universe from the point of view of an engineer, disregarding such obstacles as laws of gravitation and relativity. At the same time, he started to dream about going round the world. After graduating, having earned within 4 weeks a little sum of money for the most necessary things, having $28 in the pocket, he leaves for California. By the time he approached Los Angeles, he had 27 cents left, and he found a job in American manufactory as an engineer of electric motors development. Soon he moved to another company, Robbins and Mayer, in Springfield, Ohio, where he worked under Vronson. In 1938, Kron devoted to him a book tensors application to analysis of rotating electric machines. In 1926, Kron came back to California, and, having $300 and a textbook on differential equations in his knapsack, boarded a tanker bound for Tahiti. After several weeks on Tahiti, Kron left for Fiji. While travelling, he devoted his afternoon hours to studying maths. After Fiji Islands, he headed for Sydney, where he stayed for a while to earn money for the further trip through Australia and then to Asia. He wrote, "During the travelling, I started to figure out basic ideas of multidimensional vector analysis. Working every day with maps of unknown territories, I got the similar picture of engineering patterns, such as electric machine, or a bridge, or a plane, fixed in my mind. I saw them as a network of spaces, connected into the whole, just like numerous countries, islands, and continents, which are connected with interlacing of roads, laws, and traditions. If the connection between different members disappears, there also disappears something that turns 48 independent states into United America, or thousands separate details into a plane. Some years later, I found out that mathematicians had already made such kind of calculations, called tensor analysis. The further Kron's way went through Borneo, Manila, Hong Kong, and Saigon, where he started for Burma, and then to Calcutta. Having crossed India on train, he reached Karachi. He crossed Persian Gulf on board a vessel, visited Baghdad, Damascus, Cairo, and from Alexandria came to Constanza, Bucharest, and then to his parents, Tobiah Ma. Kron spent several months at home, studying and courting his wife-to-be Anne. After returning to America in the end of 1928, he started to work in Lincoln Electrical Company in Cleveland, and in 1930 he published the first of his more than 100 scientific articles. This work, called Generalized Theory of Electric Machinery, 9, started the series of his works, representing more and more detailed analysis of machines and systems. He suggested an idea that all types of electric machines should be special cases of a generalized machine, and understanding of the general machine should cause invention of new types of machines. After he had moved to Westinghouse's company to Springfield, he wrote his second work, 10, devoted to consideration of a coil conduct in an air gap under effect of a sine field. During the American Depression, Kron, together with his wife, comes back to Bayer-Meier, where he continues studying maths, and in particular, for the first time, deals with non-Riemannian geometry. He found analogy between abstract notions and complex interaction of electric, magnetic, and mechanical forces in machines, and in 1934 he wrote his classical work Non-Riemannian Dynamics of Rotating Electrical Machinery, 11, which in 1935 was honoured with the Montefiore Prize of the University of Liège. This work caused at once broad discussions and contradictions. Using mathematical notions in such a way nobody done before, Kron proposed a new meaning for equations and settled rules, and that was the reason for many specialists to criticize his work, considering them unreasonably complicated and unsuitable for practical use. When Kron first proposed his ideas, there were no big computers, and engineers were not much interested in big systems. It took time for their significance to be appreciated. Kron always aimed at his theories being applicable to the largest possible range of phenomena, strove for maximum generalization. That's why his methods were more complicated than a separate problem required. This, in particular, is one of the reasons why Kron's methods are not widely spread. Engineers, dealing with a single particular machine, prefer to use simplest methods and feel little interest to elegant, generalized Kron's theories. Since 1934 till his last days, Kron was working in General Electric Company, where he dealt with electric machinery, power generators, and computers. Within the period from 1936 to 1942, Kron, working hard, at the same time publishes in General Electric Review numerous articles devoted to construction and utilization of equivalent electrical circuits for different kinds of machines and systems. These articles were published as his third book, Equivalent Circuits of Electrical Machinery, 12, in 1951. His previous books, Tensor Analysis of Networks and Short Course of Tensor Analysis for Engineers Electricians, appeared correspondingly in 1939 and 1942. In 1942, Kron was transferred into Steam Turbines Department, where he worked at studying tension, appearing in Steelworks. In 1945, he began working in the research laboratory, where he solved problems of temperature distribution, nuclear reactors control, and so on. In the lab, Kron had worked up to 1963, with a small pause from 1950 to 1953. From 1963, he was connected with Engineering Analytical Branch, where he retired at the age of 65. He died after a short disease on the March 25, 1968. Kron was a bright personality, a pioneer, whose achievements were appreciated by a few in the time his works were first published, but whose methods of large-scale systems analysis are widely used now. His awards include the already mentioned Montefiore Prize. He is an honorary M.Ing. of University of Michigan, 1936, an honorary doctor of Nottingham University, 1961, a patron and honorary member of the Tensor Club of Great Britain and Research Association of Practical Geometry in Japan. Kron's eccentricity is the result of his tensor point of view. Tensor methodology brought him to working out of many powerful methods of analysis. Everything done by him could be conditionally divided into three parts. 1. Generalized theory of electrical machinery, analysis of power transition systems and diacoptics, the piecewise solution of large-scale systems, which usually applied in a simplified matrix form. 2. Tensor philosophy and mathematics that came into collision with indifference and misunderstanding. 3. Works on adaptive wave network based on 1 and 2. There are few publications on the last part of the investigation, although Kron in his last years works discussed in general the principles and the results received. The first two interdependent parts represent a rather full theory. Let's mark, first of all, that engineers are ready to accept results which join easily existing technologies and have no desire to deal with some abstract theoretical research that tensor methods may seem. But tensors have very special properties which allow to consider them being certain essences. Let's consider an example of a vector, which, as is known, can be shown graphically as an arrow. If we introduce a coordinate system, we can define the vector components and write them down in matrix column or matrix line. But we cannot identify matrix and vector itself. When we change the coordinate system, the vector components change as well, so we would deal with different matrices. But the vector remains the same, irrespective of coordinate system changes. Thus, a vector is not just a matrix. Actually, it is not a matrix at all. This is objective essence, which can be represented by an infinitely big number of matrices, each corresponding to a certain coordinate system. So when we move from one coordinate system to another, vector components transform in accord with a special rule which reflects objectivity of this invariable essence. Vector is an example of the simplest tensor of the first rank. In three-dimensional space, it has three components, corresponding to three axes of coordinate system. In n-dimensional space, it has n component. Tensor of R rank has actually the same properties as vector does, excluding the fact that its number component equals nr, and for r larger than 2 it cannot be visualized. The decisive statements are: 1. Tensor reflects objective reality. 2. Its components transform in accord with a special rule when the coordinate system changes. The tensor property, 2, shows that in some technical structure-behavior equations are most convenient when they are written down in tensor form as tensor properties, to which physical essences correspond, neither appear nor disappear while transforming. In his generalized theory of electrical networks and machines, Kron demonstrated applicability of this approach of considering tensors' physical nature. The basic Kron's idea on tensor analysis application is that two different networks, which have the same branches, are considered to be two different coordinate systems of one and the same physical essence. The idea that network is the set of branches bound up into a single whole through tensor of joint brings us to the following fundamental conclusion. Tensor of joint within transformations can be interpreted as tensor of transformations joining different subnets into one big network. One of the most significant achievements of Kron is his theory of non-Riemannian dynamics of electrical machinery. The outstanding importance of this theory lies not just in inventing tensor of joint, which shows possibilities of the entire approach in creation of general machine theory, but also in receiving such solution procedure that would transform dynamic systems equations for a statistical case. And through tensor transformations, from a machine with fixed axes, we can get equations of any rotating machine. The starting point for equations describing behavior of electrical machines of any type is Lagrange dynamic equations, which, as is known, set up proportion between generalized moments and generalized forces. Lagrange equations can take tensor form only when usual differentiation is replaced by so-called covariant differentiation, which takes into account change of component tensors at parallel transfer within curvilinear Riemannian space. However, usual covariant differentiation formula can be applied only in case of holonomic coordinate systems with geometrical connections, that is, connections, depending only on mutual disposition, not on speed. In non-holonomic systems there appear additional members, but Kron successfully got over this obstacle, having shown that in case of electrical machine additional members behave just like normal tensors, but their presence in covariant differentiation changes geometry of space from Riemannian to non-Riemannian. Thus, Kron managed to get from Maxwell-Lagrange equations engineering formula for calculation of any electric network, having overcome non-holonomity nuisances appearing when electrical axes change, by a simple transition from Riemannian to non-Riemannian geometry. In his further publications, Kron kept on improving the theory of transformations, applying it to various types of machines, obtaining the theory generalization by integrating results into the theory of piecewise solution of electric network and systems, diacoptics. Diacoptics was proposed by G.K. On in the beginning of 1950. The basic idea of diacoptics consists in a system solution by tearing it into isolated parts. The total solution of the whole system is received from the earlier solved individual torn parts. The second step is aggregating the parts by transforming solutions for the parts received earlier. The method of tearing was applied by Kron for determining equations of a completely torn model, which he called primitive. It is usually the simplest, disconnected system. Solutions of separate subsystems, forming the primitive system, and consequently the resultant solution, can be exact or approximate, can represent linear or, with certain precautions, non-linear systems. They can be expressed in the numerical form or in language of matrices, their elements being real and complex numbers, functions of time, differential or other operators, and so on. Kron, using example of numerous problems, convincingly proved that the method of tearing can be applied to solve algebraic equations, equations in usual and partial derivatives with different boundary conditions, problems on finding out eigenvalues. The method assumes continuous expansion and generalization. This process, according to Kron, is similar to skyscraper construction by erecting a steel framework first, and only after that filling room between beams the way it is required. 3. The great advantage of the method is saving calculation time. For big, intricate systems typical is the problem of matrices manipulations with big number of lines and columns, form tens to thousands, which takes many hours of work, even from modern computers. If we use diacoptics, a system tearing on n parts saves time at matrices manipulations too. The value, where t is the time of usual, without tearing, manipulation. Kron's diacoptics is based on several key principles. 15. The first one requires a complete record of all equations for generalized forces and responses for them, knowledge of additional equations for responses and interrelations that exist between forces and responses. In other words, the definition the equation of state of some physical system presupposes existence of set of equations whose number equals to the full number of forces and responses in the system. In a similar way, the equations of solutions presuppose existence of the same number of equations. Such kind of calculations is carried out automatically by writing down equations in tensor form. The excess of equations is more than compensated by the advantages given by full mathematical model, and first and foremost, the possibility of tensor apparatus application. The second principle lies in utilization of electric network model for recording equations of forces and responses. Electric networks exist on paper, so there is no need in their physical realization. They are just easily observed models of more general topological notions, forming Kron's method of reasoning. The third key moment is the discovery of an orthogonal nature of electric and other types of networks, having always non-singular, square matrices of transformation. Due to the use of configuration space of generalized forces variables, side by side with space of responses, orthogonal to the space of force variables, there is an opportunity provided for the change from complete equations of state to complete equations of solution, and vice versa, at any stage of investigation. The most important key notions are the notions of tearing into small parts of complex systems on arbitrary number of subsystems, and a reversed notion unification of them into initial or any other possible system. It should be noted that topology, the science that deals with properties of interconnected spaces, originates in Kirchhoff research which concerned electric currents transit through a network. Here we could have concluded that Kron's approach is just a practical application of a certain branch of topology. However, it's not like that. Actually, topology studies only those network properties which stay invariant during wriggle, protraction or torsion, rubber geometry. The properties that stay invariant during networks tearing into isolated parts lie outside topology interests. As opposed to topology, the theory of tensor analysis and piecewise solution of complex physical systems is primarily based on the use of notions which stay invariant, when the network of spaces breaks up into initial space components, and after that join into all kind of configurations, including initial network. This radically new point of view declares that we can move from equations of a certain possible configuration to equations of any other configuration composed of the same components, using the system of non-singular matrices of transformation, forming a so-called group of connections. It is the representation of the group that Kron called tensor of connection. The key notions transformation, invariance, group form a base for application of tensor analysis of complex systems, which before Kron was applied in classical physics for problem solution in the theory of fields of various nature and dynamic problems. Depending on the problem type, invariant could be either full conductive power in the circuit, or a part of intake, or a set of voltages applied, and so on. The tensor approach breaks down barriers between the notions equations of state and equations of solution, which first seem isolated, but actually are dual, by connecting them with matrices of connection tensor, convenient to be calculated on electronic computers. Physical systems used for connection may be of absolutely different nature. They may consist of devices where electric, thermal, chemical, mechanical phenomena take place in their poured speed key. Non-physical problems, which can be represented by tensor equations, can also be solved by the method of diacoptics. In works of Kron and his followers, there are given numerous examples of calculations in various fields of engineering, including force constructions calculations, aerodynamics, systems of control, modern electronics, and among non-physical systems, economic problems, operation analysis, and so on. Tensor method has a number of advantages. One of them is what Kron called mass production of solutions. Indeed, is a piecewise torn system, consists of similar, or a few repeated forms. One solution for the subsystem is applicable for most parts. The process of connection is often the same for most analogues devices. The system solutions can be stored up either in numerical form or in the form of structural tensors, so that they could be used again every time there appears a need in solving the bigger system. Standard solutions can be stored and then applied to problems of various types, a procedure not arising from other methods of solution. When a large-scale system is already calculated and its certain parts change after that, the same change can be carried out on the corresponding parts of the solution. There is no need in analyzing and solving the changed system every time anew. We should just make calculations in the changed part. Thus, tensor solutions can correspond the same type of growth and evolution the analyzed system overcomes. As for applying models as electric circuits, Kron wrote, 15. Evidently, from a strictly scientific point of view, the model of physical phenomena should be either algebraic or geometric, topological. The author, being an engineer-electrician, neither mathematician nor topologist, should express his ideas in terms of the science most familiar to him. Of course, the use of electric circuit model is not absolutely necessary. It's just a ruse to substitute records of extremely big number of equations and manipulate with them. It is really a ruse that verges on art. Kron constructed a lot of models of electric networks for the most various types of problems: distribution of a thermal current, wave equation of Schrödinger, current of a liquid, neutron diffusion in a nuclear reactor, stresses in elastic girders, forces of basicity in polyatomic molecules, lines of electric power transfers, systems of linear and non-linear equations in usual and partial derivatives and others. However, after his death, there appeared no new models of electric circuits proposed by other authors. Along with electric circuits, Kron used model representations in the form of algebraic diagrams of Ross, which allow to visualize the structure of problems, requiring for their solution the use of interconnected, multidimensional spaces. The possibility of constructing models reflecting the problem structure was also found by Kron in using theory of groups and symbolical logic. During the last decade, Kron was intensively working on the theory of self-organized polyhedral networks or wave-automatic machines. Here, the starting point in Kron's reasoning is still his belief that even linear, one-dimensional, network contains much more information about modeled problem than just a set of points in space. A description, typical for usual mathematics, as the network branches penetrate surroundings of a given point, and thus it turns out to be connected with the nearest and more distant environment. Further generalization consists in considering a network, consisting of planes, where each plane connects 3 or more neighbor lines along with linear network, whose branches are one-simplexes, connecting 2 neighbor points. Now, in n-dimensional space there appear an additional network consisting of such triangle planes, 2 simplexes, which, as well as in case of linear network, can form open and closed paths. Since 4 triangles with common edges form tetrahedron, 3 simplex, it becomes evident that even more complete information can be received from the neighbor surroundings of the given point if we fulfill utterly n-dimensional space with tetrahedral network forming open and closed paths. This process can be continued provided the dimensionality of elements, p simplexes, composing resultant additional network, will grow until the entire n-dimensional space is fulfilled with n plus 1 various networks. The initial system of points can be considered to be 0 simplex. In combinatorial topology, such universal structure, composed of 0-122 n-dimensional, interconnected networks is called polyhedron. However, there are no such notions as either impedance or current and stress in combinatorial topology, but Kron accepted the point of view that area of each p-simplex is represented by its impedance. Then, to complete description of n-dimensional space, Kron also invented a notion of mutually orthogonal to the initial, dual-to-it polyhedron. It turned out that with each simplex of the initial polyhedron, there is connected n p-simplex of dual polyhedron, and these 2 simplexes represent a certain part of n-dimensional space, and now surroundings of a separate point are completely described by n plus 1 different doubled simplexes of various dimensions that surround the point. Thus, it is accepted that 2 non-brisk polyhedrons, initial and dual, represent the set of independent variables more complete, even in the case when there is given a comparatively small number of points. However, neighbor surroundings of each point deliver now more information for analysis. The task was to revive the received polyhedral network in accord with accepted methodology. The fact is that electric current cannot flow in polyhedron, as current vectors do not satisfy Stokes' theorem while passing boundaries of networks with different dimensions. Vector linear integral should on closed trajectory be equal to surface integral of vector curl. However, this theorem is satisfied by a full set of Maxwell equations. Thus, a complete electromagnetic wave, characterized with 4 types of adaptive parameters E, H, B, D, can spread through a polyhedron and the one dual to it. Trying to satisfy Stokes' theorem in wave passage through networks of different dimensions, Kron determined the fact, well known in geometry, that even-dimensional spaces behave differently from odd-dimensional spaces, and therefore, in polyhedron, there should be invented 2 complete networks of various physical nature for generating one electromagnetic wave. In this connection, Kron invented the generalization that all even-dimensional spaces are constructed of magnetic material, while all odd-dimensional networks of dielectric material. In dual polyhedron, the physical role of spaces of even and odd dimensions is mutually reversed. Thus, for one electromagnetic wave diffusion, there should be 2 networks of p and p1 dimensions, even and odd. Therefore, n-dimensional polyhedron and dual polyhedron comprise n 2 sequence of space waves, each spreading through spaces of growing dimensions. The constructed polyhedral structure represents a multi-dimensional space filter with a fixed set of natural frequencies. If we make up our minds to model, to adjust, some function, the problem would be solved with the least mistake for the functions close to proper solutions, corresponding to this certain set of frequencies. Kron asked himself a question: if it was possible to construct such multi-dimensional space filter which would help to adjust not one, but a big number of functions simultaneously, or, in other words, if it was possible to construct such a structure which could oscillate not only with one certain set of frequencies, but with all possible frequencies. Such structure should differ from a usual filter with discrete spectrum by having a continuous spectrum. It was found out that this problem could be solved if we placed straight and dual polyhedron into stationary magnetohydrodynamic plasma, accompanied by 4 additional adaptive parameters which characterize densities of electric charge, magnetic fluxes, and corresponding currents, P-P-J-J. The presence of already 8 types of adaptive parameters in each P network gives no promise that such structure will be able to oscillate. It is also necessary for various straight and dual networks to be connected by ideal transformers. Such non-mechanical oscillating structure, having neither velocities nor moments, was called by Kron oscillating polyhedron, which represents the simplest possible form of self-organizing automate of dynamo type, that is, whose operation is based on complex interaction of generalized rotating electric machines, dynamos. Oscillating automate can be a model for solving numerous statistical, economical, and physical problems of large dimensions. 16. Kron demonstrated possibilities of self-organizing automate by an example of simulation, adjustment of 6 arbitrary functions on 4, given on a plane, points. The task required was that polyhedron could simultaneously reproduce all 6 proposed functions, plus their first and second derivatives, as exactly as it was possible, without the model change every time the adjusted function was changed. The model consisted of 13 structures, representing generalized rotating electric machines, with 13 usual and 13 quadratic axes. In particular, 4 machines represented a function, 6 its first differentials, and 3 second differentials.
17.
Calculations showed very high accuracy of adjustment, especially in case of oscillating polyhedron. It is important to underline that all 6 functions gave the same results with equal accuracy without changing model, when the functions changed, for which the evaluations were done. A big number of adaptive parameters, waves, adjusted themselves to the change of boundary conditions. Thus, self-organizing polyhedral automate is, actually, a universal model, able to simultaneously evaluate any number of functions. When there is a fixed set of data, matrix data or independent variables, Euclidean polyhedral automate with straight p-simplexes can first of all be applied for receiving numerical solutions in multidimensional problems, such as multidimensional adjustment of curves, interpolation, data smoothing, generalized harmonic analysis, and others. With the help of oscillating polyhedron, there can also be studied the processes of nonlinear programming, problems of reliability, recognition of forms, and others. The further way of generalization proposed by Kron consists in insertion of polyhedrons into moving magnetohydrodynamic plasma. In this case, straight lines, planes, cubes, and so on in polyhedron become curved lines, planes, cubes. First, usual Euclidean spaces and simplexes with metrics set by the network elements are changed to non-Euclidean, Riemannian or non-Riemannian simplexes with the help of affine connections of various types. These bent elements of the network cause appearance of new parameters, characterizing their curvature and torsion. Such a complex automate is useful first of all for studying the very magnetohydrodynamic plasma. The possibility appears to analyze many phenomena which occur in the plasma, proceeding not only from usual field description, but from the discrete one as well. Polyhedral structure, immersed into multidimensional fluid, is considered to be a stationary coordinate system, where there are projected moving fragments and waves. To be more exact, they're linear, surface, volume, and so on integrals. Although polyhedron and plasma, taken separately, are described by a comparatively small number of variables, additional multidimensional p-networks, nevertheless, provide detailed information about all derivatives in various directions of all operating surfaces. Each p-simplex can be considered in details on the analysis basis of p-dimensional field distribution with the help of tensors of p-rank. full description of plasma can be replaced by consideration of multidimensional networks, consequence of growing dimensions transmittance. Networks unite into one operating system, a big number of multidimensional rotating electric machines, excited by electrostatic and magnetic flows, and possessing liquid and gaseous rotors, each having immediate speed, moments, and other attributes. Tensor notions can be used for studying stability of plasma, considered as networks of generation, transmittance, and distribution of energy types. The already worked out tensor notions point at existence of new types of stabilizing forces, which are not taken into account by usual non-tensor methods, and which can be unknown to practicing engineers. The Kron's idea about polyhedron, which in problems of cognitive type, such as recognition of images, can play the role of artificial brain, where each neuron is represented by a magnetohydrodynamic generator, generalized rotating electric machine, is almost the most prospective direction for development of Kron's polyhedral wave automate. Such type of artificial brain, dynamo type, or a type of energetic network, is based on a foundation different from the models of artificial brain, presently being developed on the basis of commutation networks, switching networks. There are very few publications on this research, although Kron discussed in general the principles and results received in his various works of last years. Kron himself considered this part of work to be the crown of his research, especially the idea of crystalline computer, using analogy between crystal optical properties under effect of light source and mathematical properties of multidimensional polyhedron, submerged into plasma. Very important is the fact that polyhedral system assumes statistical interpretation. That is, non-brisk network represents moments distributive functions of various types, and distributed waves can be treated as presentation of means, variations, correlative functions, spectral density, and many other notions. For description of a big number of rotating electric machines, Kron widely used the notions, in their basis having statistical nature, such as boundary and free energy, entropy, thermodynamic density, and others. Here could be seen an extremely interesting connection between Kron's self-organizing polyhedral structures and those fruitful ideas, which are being worked out by the winner of the Nobel Prize, Prigozhin, lately having become widely spread among representatives of various sciences and trends. 18. The idea of developed by Prigozhin, a specialist on non-equilibrium thermodynamic systems, approach is expressed in the title of one of his books, Order from Chaos. He convincingly showed that under certain conditions open non-equilibrium systems, exchanging energy flows with environment, can arbitrarily turn from chaotic, disorganized state to organized system, and can stay in such state till conditions change. Thus, Kron's adaptive polyhedrons, realizing non-linear, multidimensional statistical phenomena, can serve as ideal models for analyses of such complex systems, changing from disorganized to organized state. Adaptive polyhedrons, transforming any, including chaotic, spaces of states into automatically organized spaces of solutions, can serve as models for quickly developing lately theories, using such notions as fractals or regulated chaos. Actually, tensor methodology of Kron gives unlimited opportunities for constructing various kinds of models, and their value consists not just in appearance of common algorithm for their consideration, but also in possibility of receiving new knowledge. Tensor approach can also be applied for solution of such important problem as forming databases and knowledge. Tensor databases. Various signs of some information massive can be considered as tensor essence component, projections, into this or that coordinate system. System of knowledge, transition. From one massif to another, when the required sign changes, can be carried out on the basis of tensor transformation rules, thus excluding the need to search information every time anew. A possibility to keep ready solutions for different subsystems, and, if necessary, carry out synthesis of solutions, form a basis for constructing and controlling systems of automation of new technical means and technologies projecting, including automated projecting of robototechnic systems. Although Kron himself wasn't engaged in the sphere of management, his ideas formed an important part of conceptual notions, principal system notions, such as idea of change, existence of alternative methods for receiving results, strong influence of environment and others, find adequate reflection in the Kron's theory. The list of examples of tensor methodology application could be ever continued, but the already given review shows fully enough the idea about strength, flexibility, and breadth of tensor approach to solution of complex systems. The author is convinced that we should keep on studying the scientific heritage of Guy Kron, especially it concerns his works on self-organizing polyhedrons, develop his methods of tensor analysis and network syntheses as a common model basis, make them available for wide range of specialists. Literature 1. Electrochestvo, 1969, G. No. 1, p. 2. Electrochestvo, 1950 G. Nobor 12. 3.
Eddy, P. Kuznetsova, M. SOV. Radio, 1978. Translation from English, Pod Red.
Lee Kusina, Kron G. A Short Course in Tensor Analysis for Electrical Engineers, N.Y. Wiley, London, 1942. 4. Kron G. Primenenie Tensornogo Analyzer fi Elektrotechniki, Trans. From English, Pod Red. Miravica P.V., M. Gostikizdat, 1955. 5. Kron G. Isledovanie Slojnik System po Chastium, Diarcoptica, Trans. From English, Pod Red. Avbaranova, M. Nauka, 1972. 6. Petrov I Tensornaya Metodologia fi Teorii System, M. Radioishviaz, 1985. 7. Nan Gabriel Kron and System Theory, N.Y. Schenectady, Union College Press, 1973. 8. Kron G. Generalized Theory of Electric Machinery, A.E., American Institute of Electrical Engineers, Trans, V49, 1930, p. 666. 9. 10. Induction motor slot combinations, rules to predetermine crawling vibration, noise and hooks in the speed, torque curve, i.e. Trans, Vol 50 and 1931, p. 757. 11. Kron G. Non-Riemannian Dynamics of Rotating Electrical Machinery, J. Math, Phys. 1934, V13, No. 2, p. 103. 12. Kron G. Equivalent Circuits of Electrical Machinery, N.Y. Wiley, 1951, London Dover, 1967, p. 278. 13. Journal of the Franklin Institute, V. 286, Nov. 6, 1968, 14. Hoffman B. Kron's Non-Riemannian Electrodynamics, Reverend Mod, Phys. Einstein's Birthday Commemorative Issue, 1949, V21, p. 535, 15. Kron G. As Set Principles to Interconnect the Solutions of Physical Systems, J. Apple, Phys. 1953, V24, p. 965, 16. Kron G. Self-Organizing, Dynamo Type, Automata Matrix, and Tensor Quarter-Array, 1960, V11, No. 2, p. 42. 17. Kron G. Multidimensional Curve Fitting with Self-Organizing Automata, J. Math, Analysis, and Apple, Phys. 1962, 18. Iprigozhin, Estenges, Poriadok Iskaiosa, Mir, 1968, 19. Arm Kronova, Fractali I Chaos v Dynamiczne Systema, M. Postmarket, 2000, 20. Kusin LT, Armensky AN, Petrov I, Abramov Du, Ermakov, and Tensorny Banki Danik. Eyes V. Vuzov, SSR, Priborostroyenia, 1984, No. 6, p. 38.